On example 5, can segments with the lengths 4.3 feet, 5.2 feet, and 6.1 feet form a triangle? If so, would the triangle be an acute triangle, a right triangle, or an obtuse triangle? All right, so we're actually going to combine up two different things here. And the first part of it is, hey, can this thing actually make a triangle? Can it form a triangle? What do I use in order to see if three numbers can form the side lengths of a triangle? I use the triangle inequality. Remember, that means that if I add up two sides of our triangle, that two sides has to be greater than the third side. In practice, when I have three numbers already, all I have to do is check the two smallest ones, see if it adds up to something bigger than the third side. That's what I'm going to check first, triangle inequality. Do I even have a triangle? So my two smallest sides here, we've got 4.3. And I have plus 5.2. I want to see, is that thing, in fact, greater than 6.1? Well, I can already see I got 4 and 5. That's 9. 9's bigger than 6. That's definitely going to work out. But actual numbers here would be 9.5, definitely greater than 6.1. So, yes, we can make a triangle. Yes. A triangle. What is this thing? There's a big smudge. Okay, a triangle can be formed. Now the next question is, what type of triangle can be formed? In order to determine that, we will use the Pythagorean identity, starting with our largest side here, which is the 6.1. So we're going to see what is the relationship between c squared and a squared plus b squared. Right, so I'm going to have my 6.1, which I will square it. Is that greater than or less than or equal to 4.3 squared plus 5.2 squared? All right, we will pull up the calculator for this thing. Yes, we will be right there. All right, and we had 6.1 squared, 6.1. We're going to square that thing. All right, and we've got 37.21. Okay. And then let's go back and 4.3, 5.2. Square those. 4.3 squared plus 5.2 squared. And we get, boop, 4553. All right, we can definitely see that the c squared here is less than the a squared plus b squared. So the conclusion, we have ourselves an acute triangle. It's less than, it's acute. So let me just illustrate what I was talking about before. If we accidentally put down, just out of habit, our a squared and our b squared first. Well, in that case, what we would have written down is 45.53, saw that it was greater than 37.21. And can you see how I can accidentally make the conclusion that this is an obtuse triangle? Huh? Yeah, so like I said, get in the habit of writing the c squared part down first. All right, one more algebraic-based question here on example 6. This one's a fun one. The sides of an obtuse triangle have the lengths x, x plus 3, and 15. What are the possible values of x if 15 is the longest side of that triangle? I'm going to recommend the first step that we take is to draw a picture for this thing. So we know it's supposed to be an obtuse triangle where 15 here is our biggest side. So just sketch yourself out some sort of triangle, an obtuse looking triangle. Oh, it's glorious, right? So 15 being our longest side. And then we have two other sides. One of them is x and the other one is x plus 3. All right, and we want to know what are the possible values of x that makes this thing obtuse. All right, before I even start that part of it, though, I'm going to do the same thing that I did up here on this one, and I want to use the triangle inequality. We want to see, well, first of all, what are the possible values of x that even make this thing a triangle? I don't even care about it being obtuse. First of all, I want to know what makes this thing a triangle. And ordinarily, I would have to take, let's say, any two of these sides, add them up, and it would have to be bigger than the third side. But I only have to worry about one inequality here because we already know 15 is the biggest. So these two, x and x plus 3, they have to be greater than, when we sum them up, the 15. So this is triangle inequality. X plus 3 is got to be greater than 15 in order for it to be a triangle. So let's solve this inequality for x. Got two x's. Subtract over that 3. 2x is greater than 12, which means x has got to be greater than 6. Is that it? It's just x is greater than 6 and you're done? So can x be something like, I don't know, 400? Well, no, x can't be 400. We said that the longest side has to be 15. So there's a little bit extra stuff here that we have to take into account. Since 15 is the biggest side, that means that x has to be less than 15, first of all. But it also means that x plus 3 has to be less than 15. If I solve that one, subtract over the 3, x has got to be less than 12. And you can see that this x is less than 12 is more restrictive than the x is less than 15. That's the one that we're going to keep. Here's another way to see that. I'm going to put all of these on a number line so we can easily visualize what the solution is supposed to be. So we have a 0. Let's say that here is 6, and then here would be 12, and then we got our 15 right there. Right? Is 15? Yeah. All right, and so as far as inequalities go, let's say, I'll choose the blue one. Greater than 6 is open circle, moving to the right. And how about green? Less than 15, open circle on 15, moving to the left. And then one last one, open circle on 12, and then also moving to the left. Boop. And then we want the overlap of all of these pieces. The overlap of all of these pieces is going to be right here from 6 to 12 with open circles around them. Boop. Written as a compound inequality, that goes like this. 6 is less than x, which is less than 12. This represents every possible value of x that you can make a triangle, right? All possible triangles. It's all possible triangles where 15 is the biggest side. Some of these triangles are going to be acute, some of them are going to be obtuse, and exactly one of them will be a right triangle, where c squared is equal to a squared plus b squared. Okay, so that's going to bring us to the second part of this, where now, of those numbers that we just found there, which ones make it an obtuse triangle? To be an obtuse triangle, we know that c squared is supposed to be greater than a squared plus b squared. Our c is 15. It's the biggest side. It's got to be bigger than x squared plus, in parentheses, x plus 3 squared. Our a squared and our b squared. So what we have here is what is called a quadratic inequality. In quadratic inequalities, you don't solve exactly like a quadratic equation, as we're about to see, but the initial process is the same. We still have to make the thing equal to 0, not really equal to 0, right? Because we don't even have an equal sign. 0 on one side, everything else on the other side, so that we can try to factor this thing. So on the left-hand side, we got 225, supposed to be greater than x squared plus, and now when I expand this x plus 3 out, it's foiling x plus 3 times x plus 3. When I multiply the first terms together, I get x squared. X times 3 would be a 3x, but also whenever I do the inside terms, I get another 3x. Adding those together, I get 6 of them. And then finally, the last terms, 3 times 3 gives us plus 9. So the shortcut on that, if you didn't know, is you square the first one, boop, you square the last one, boop, and to get this middle term, you multiply these two, x times 3, and then you double it. You double it because whenever we FOILed it out, we had 2 of them. All right, anyway, let's combine our like terms, get everything on one side of the equation here. 225 is greater than 2x squared plus 6x plus 9. Subtract over the 225 to have 0 on that side. 6x, let's see, 9 minus 225, negative 216. Okay, now, always, you want to pick up on some of these kind of skills. Notice that everything in your equation is even. If it's all even, you can make your equation, or inequality in this case, a little bit easier to work with if we divide everything by 2. Makes our numbers a little bit smaller. So we have 0 is greater than x squared plus 3x minus 108. So remember that in order to solve quadratic equations, you set the thing equal to 0 and you factor it and you apply the product property that a times b is equal to 0, which means that one of the factors a or b had to start off being 0. That does not work whenever you have yourself an inequality anymore. So what we do instead is that we solve a related equation and then we use it to find what are called critical numbers. It's going to be the boundary points of our inequality. We pretend like this is an equation, first of all. Whoops. And we solve that just like we would solve any quadratic equation by factoring or quadratic formula or graphing or, you know, asking your best friend, your smarter best friend. All right, so we know that this and this, x times x gives us x squared. This position times this position must be equal to 108, negative 108, and then has to add up to 3. So what times what gives us 108, and when we subtract them, because we have a negative sign there, when we subtract them, we get 3. I think we've got a 9 and a 12, because 9 times 12 is 108, and if I subtract these, I would get 3, and I need my 3 to be positive, which means the 12 has to be positive, and the 9 has to be negative. There we go. We have successfully factored this thing, and then, you know, that's not done yet. We still need to get our values of x. If x minus 9 was equal to 0, that means that x has to be equal to 9. Or if x plus 12 was equal to 0, that means that x has to be equal to negative 12. These are what are called critical numbers. These are going to be the boundary points of the inequality that we were trying to solve up here. And in order to see, so in other words, our answer is either going to be in between those two numbers or it's going to be on the outside of those two numbers. And let me explain why. If I had, let's say, we know that a quadratic, when we graph that thing, it makes a parabola. So maybe I graph myself a parabola right here. What we're trying to do here is that we're trying to, we're doing an inequality, which means I either shade inside of it or I shade on the outside. If I shade on the inside, notice that it hits the x-axis here in between. Maybe I choose this pink one. It hits the x-axis in between the two x-intercepts, right? All right, if I had shaded on the outside, maybe I pick another color. How about orange? Okay, if I pick orange, maybe I shaded on the outside of this thing. If I shaded on the outside of this thing, where it hits the x-axis, this time it would be on the outside of those two numbers. Essentially, that's what we're about to do here. The two numbers, the two x-intercepts, are our critical numbers. They're going to be the boundary points of our inequality. So I'm just going to take a number line here. I'll put maybe 0 right here in the middle. I've got a 9 on one side. I've got a negative 12 on the other side. And I know that these have to be open circles. because we have 0 is greater than right here, not greater than or equal to. Yikes. Yep. All right. My answers are either going to be in between those two or it's going to be on the outside. See, just like what we have right here for this parabola kind of shape. The easiest way to be able to tell that is to pick a number and put it into the inequality and test it out. What do you think is the easiest number to test out? That's right, 0. So let's test 0. So we'll plug that into the inequality. This one right here, this inequality right there. We're just going to plug it in there. Actually, you can plug it in any of the ones that came prior to that one. That one's just going to be the easiest. So I have 0 is greater than 0 squared plus 3 times 0 minus 108. And I want to see, is that a true statement or is it a false statement? On the left side, still 0. 0 squared is 0. Plus 3 times 0 is 0. And I'm left with negative 108. Is 0 bigger than negative 108? Yes, that's a true statement. Which means that our solutions are everything that takes place in between them. So 0 worked, which means that everything in between here is going to work. Our parabola would have been something like this. And we're shading on the inside of that. And where it hit the x-axis, those are the solutions that we would have kept. Our solutions then are from negative 12 is less than x, which is less than 9. Now, algebraically, that's how this inequality in orange right here solves. Geometrically, though, not all of those solutions make sense. Because remember, if I come back up here, we said that the only possible triangles are from 6 to 12, which means I have to chop off some of these triangles, right? I have to chop off some of these numbers. As a matter of fact, let's say, for example, if I, maybe I pick out blue here, I know right here is supposed to be the number 6. I got to get rid of this stuff. And then over here is the number 12. All of the triangles live in that interval from 6 to 12. And what we can see here from the overlap is from 6 to 9, those are all of our obtuse triangles. So from 6 is less than x, which is less than 9. Any value in here makes this thing an obtuse triangle. So let me just illustrate that. Let me show you that that's absolutely true. Let's pick a number between 6 and 9. It can't be 6. It can't be 9. So how about 7? So let's test out x equals 7. Well, in our obtuse triangle, we know that this longest side was 15. Our x was over here. And then on the bottom, we had x plus 3, so that would be 10. So I would have 15 squared, boop, boop, boop. Compare that to 7 squared plus 10 squared. 15 squared is 225. 7 squared is 49. 10 squared is 100. I'd have 149. And I can definitely see that c squared is greater than a squared plus b squared. It totally checked out. All right. But what about all of the other numbers? Remember, 6 to 12 made all the different kinds of triangles. Well, 9 is super special. Let's test x equals 9. If I test x equals 9, what are these wavy lines? Let me get rid of them. Let me try that again. This is better. This is so much better. All right, so I'll still put the 15 here. This is 9. 9 plus 3 is 12. 15 squared. 9 squared plus 12 squared. We already know this is 225. That's 81. That's 144. That would be, let's see, 14, 8 is 2. So 5, 12, 1, 2, 225. It's equal to. We had ourselves a right triangle. Right? It's actually a Pythagorean triple. It's 3 times 3, 3 times 4, and 3 times 5. Right? And so what does that mean the other ones are? Everything else that from 9 to 12, what just happened? from 9 to 12, those have to be the acute triangles. Those are the only ones that are left over. So acute must be from 9, which is less than x, which is less than 12. Let's just check it. Let's check it with, I don't know, how about 10? So I'll put a 10 there. I'll put a 15 there. And 10 plus 3 would be 13. So 15 squared, compare that to 10 squared plus 13 squared. 225, of course? No. No. And that'd be 100. That's 169. That's 269. And now we can see that c squared is less than a squared plus b squared, and it is definitely acute. Checks out. Whew! There we go. Wow, we did a little bit more on this problem than we needed to. The answer that we were actually looking for is all the values from 6 to 9 make this an obtuse triangle. One of the ways that we could have maybe simplified the problem, made it a little bit easier, is just to simply have, well, first of all, find all the triangles. We needed to do that first, and that was from 6 to 12. To simplify this whole process, there was only one triangle, right there, boop, 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 that made it a right triangle. That number is pretty easy to find. Look at it. It was right there. It came from solving that quadratic equation. So if we solve for the right triangle first, then we could very easily test out on either side of that inequality, this inequality that we would have had here, to see if you have obtuse versus the acute side. All right? All right, so there you have it. There is the end of this lesson on the converse of the Pythagorean theorem. So it turns out the converse of the Pythagorean theorem is in fact true, that if c squared is equal to a squared plus b squared, where c is the length of the hypotenuse, the longest side, then you do have a right triangle. In addition to that, if c squared is less than a squared plus b squared, we know we have an acute triangle. And if c squared is greater than a squared plus b squared, what type of triangle do we have? Yes, we have an obtuse triangle.